I'm basically gonna walk you through another exciting topic in statistics. And you know what? Uh, Today the focus is going to be on multi-factor analysis of variance. Okay, that we also call the randomized complete block design. But you know what? I started with you on Monday, on Wednesday. I mean, specifically, I introduced the analysis of variance to you on Monday, where we are trying to compare means in different groups. And of course, I walk you through the statistical architecture of one-way analysis of variance. And of course, I actually make a distinction between analysis of variance and the regression analysis. I remember I mentioned that the analysis of variance is actually used, is more appropriate for experimental studies, situation where you actually assign participants into different uh, groups using the principle of randomization. And of course, and I said the regression analysis is basically suited for observational studies. But you know what? There are situations where we use regression analysis for experimental studies and even the analysis of variance for observational studies. But only that what you need to take note is uh, analysis of variance is well suited, for to experimental studies. Okay, I just wanted to take note of that. Now, on Wednesday, I introduced you to application of one-way analysis of variance. The one-way analysis of variance is basically complete randomized design. What do we call complete randomized design? It means we actually assign participant to experimental unit using instruction of chance. And we actually did that because we believe that doing that, allowing randomization, we actually guide against bias. But you know what? I want to tell you this, even though in most of the situations where complete randomized design is being applied, um, we realize that we normally have a very good result. But you know what? What of in a situation whereby the experimental units are not homogeneous? I'm going to say that again. The experimental units are not homogeneous. Okay, if experiment, because in the one-way analysis of variance, where we allow one-way variation, assumption is that the experimental units are homogeneous. But what of in a situation where the experimental units are not homogeneous? Of course, using a complete randomized design that we call one-way analysis of variance may not actually do the job, okay, the way we want. And that is what is actually going to lead us to today's topic, where we needed to we needed to consider another kind of design that we call a randomized complete block design. I'm going to say that again. What is the difference between what we want to do right now and what I've introduced to you, what I introduced to you on Monday and Wednesday this week? What I introduced to you on Monday and Wednesday this week is basically is applicable to situations where the experimental units are homogeneous. The moment the experimental unit, when I say experimental unit, that is a unit that actually receive treatment. Okay, when the experimental units are not homogeneous, then basically we actually need to introduce blocking in that kind of situation. And that is what leads us to today's topic that we call multi-factor ANOVA or randomized complete block design. Okay, so I need everyone to confirm if you are still hearing me clearly. Are you still hearing me clearly?
Yes.
Okay, thank you so much, and thank you for confirming that. Okay, now in the outline today, we're going to consider what we call the concept of multi-factor ANOVA. Particularly, we're going to focus on two-way ANOVA, and I'm actually going to show you how to implement the two-way ANOVA in R. Of course, the last time, when Monday and Wednesday, you were introduced to one-way ANOVA, and what I'm trying to tell you right now, the one-way ANOVA is appropriate in the situation where the experimental unit, I think I'm actually going to write that, okay, is situation where the experimental units, okay, are homogeneous, okay, are homogeneous, okay, are homogeneous, okay. When the experimental units are homogeneous, then we use one-way analysis of variance. But situation where the experimental units are not homogeneous, we have to consider, some, more design beyond one-way analysis of variance. Okay, so like I said, basically going to walk you through uh, two-way analysis of variance, and we basically, the difference between what we want to do now and what we've done before, we realize that the experimental unit is, what if in a situation where the experimental unit is not homogeneous. Okay, when the experimental unit is not homogeneous, then it means we're actually going to introduce block. Okay, we're going to introduce block. Okay, now I want to walk you through now the structure of two-way ANOVA data. And you know what, in this example, I'm basically going to, we want to look at the effects of drug, okay, on a particular response, okay. And you know what, we realize that the experimental units are not homogeneous. The experimental unit are the subjects. Of course, if you actually want to test the effect of a drug, right, you're basically going to test that on subjects. Now, situation where the subjects are not this, are not homogeneous, then it means we're actually going to incorporate into our model structure a nuisance factor. I'm going to write that nuisance factor. What do I mean by nuisance factor? A nuisance factor is actually a factor that are also, but that could potentially influence the response, even though they are not of primary of interest. What is of primary of interest right here is actually a drug. We actually want to look at the effect of a drug on a particular, we're looking at the effect of drug, when you take a look at the drug now, basically we're going to have different levels of them. Okay, we want to compare, okay, the response at different levels of drug. But you know what, we realize that the experimental unit, which happens to be the experimental unit here, which happens to be subject, are not homogeneous, and because of that, that could potentially influence the result, and that is the reason why they needed to be incorporated. Okay, so what I'm trying to show you right now, okay, I want to show you how the statistical architecture of two-way analysis of variance data is going to look like. In that kind of situation, we're going to have a cross tabulation table where we're going to say one, it means we're having two factor. If you take a look at that, And when one factor is a drug, another factor is basically going to be subject. Okay, I'm going to say that again. One factor is going to be drug, another factor is going to be subject. And you know what? In a cross-tabulated table, we're basically going to have one factor is going to occupy rows and the other factor is going to occupy column. Okay, and you know what? If you take a look at this guy here that I call grand average, is basically going to be the overall mean, okay, of the response. Okay, and when you take a look at this guy now, okay, you know, the alpha k is the effect of factor A, okay, and the beta k is basically effect of factor B. I'm going to say that again. We have a notation in a two-way analysis of variance where we have a factor A and we have a factor B. Okay, the alpha k is basically going to represent the effect of factor A, and beta k is basically going to represent effect of factor B. And you know what we're going to do? If I want to get effect of factor A, manually or mathematically, or what I'm just going to be doing, I need to find the average, okay, for that particular factor. Then I'm actually going to be subtracting the overall average from that. And with that, I'm basically going to have the factor A effect. If I want to have factor B effect, what I'm basically going to do, I also need to get the average of that particular factor B. Then I'm actually going to subtract the grand mean, okay, from that. Okay, this is to show you the mathematical way of figuring out the factor A effect and the factor B effect. Okay, now I need everyone to confirm if you're seeing the data set, the table that I'm showing you right now. If you can see that, I need you to say yes or you comment yes.
Yeah.
Okay, thank you so much, and thank you for confirming that. When you take a look at what I'm displaying now, you have subject, you have treatment, you have rate, right? Now, you know what we're looking for? If you look at the treatment side is actually the drug level. Okay, the rate is basically the response. Okay, you know what we actually want to do? We got three levels of treatment. Take a look at this. We are actually want to say we want to compare rate, which is the response across the levels of treatment, and our treatment in this situation is basically drug. We got three levels of drug. We got placebo, we got caffeine, we got trebomine. You know what we actually want to do? We basically want to compare whether the rates are the same, okay, whether there's a significant difference in the rates or in the rate, between the placebo, the caffeine, and the trebomine. Okay, if we really want to use these two data set alone, we're basically going to use one-way analysis of variance. But you know what? We realize that the subject, which is the experimental unit that is actually going to receive the drug, there's possibility there could be variations among them. And that is the reason I'm actually going to call that subject now nuisance factor. Nuisance factor in the sense that that is not, a factor that is of primary of interest to the experimenter. But you know what? We believe that if there's a variation in the subject, I'm going to say that again. If there's a variation in the experimental unit that receive treatment, then the one-way analysis of variance will not do a good job. I'm going to say that again. Before you can actually use one-way analysis of variance, you needed to actually invoke an assumption that among the experimental unit, there's no variation. I'm going to say that again. Before you can use one-way analysis of variance, okay, you got to assume that the experimental units are homogeneous. Homogeneous basically telling us there's no variation among them. But situation where we actually suspect that there could be a variation among the subjects, then we actually need to extend, we need to look beyond our model. We need to look beyond the one-way analysis of variance, which means we basically needed to incorporate that factor subject into the model. Instead of you to have a one-way, you're going to have a two-way, because of the fact that the sources of there's a new sources of variation being introduced. It's a new sources of variation will be added to the model because of the fact that the variation actually occur among the subjects. Okay, there's something I want you to pay attention to. When you look at subject 1, we actually compare all the 3 levels of the treatment. Take a look at that. When you look at the subject 2, we also apply all the 3 levels of the treatment. When you look at the subject 3, we actually compare all the 3 levels of the treatment. When you look at the subject 4, then we basically also compare all the 3 levels of the treatment. And you know what? When you look at the first factor here that I actually call factor A, which is treatment right here, it has 3 levels. The levels are placebo, caffeine, and trebomine. And when you look at the subject, which we call factor B, we also call that a blocking effect. It's block. We call that block. I remember George Box. You know what George Box said? He said, block as much as possible than you can randomize. I'm going to say that again. He encourage you to block more, okay, than you can randomize. That is what Judge Boss said. Okay, now when you take a look at what I have now, okay, if I really want to compute that manually, okay, how am I going to, for instance, I want to get the drug effect. I also want to get the subject effect. What am I going to do? And I'm going to use the formula. Now, you know what I'm going to do under the drug effect? I'm actually, I got 3 levels of them, right? The placebo, the caffeine, the trebomine. And of course, under the subject, I got how many? I got 4 subject, right? And you know what? I told you the other time that when you are talking about the drug effect, the factor A, you basically going to use what I call, let me show you. You're going to see now. I said, okay, can you say that? Alpha K, okay, that is going to be the notation for the factor A effect, and the alpha beta K is basically the notation for, for this, for the beta, for the other effect, the factor B effect. Okay, now what we want to do now, okay, we actually need to get a gram mean. Okay, the gram mean, how do we get 34? Okay, how do we get the gram mean, which is 34? How do we get that? The way we get that, we find the average of all that. We added 11 to 26 to 20, up to 32. We divided by, the total number of that. Okay, we got 1, 2, 3, 4, 5, 6. I think we basically going to have, we have like a 12, right? Now, is there anyone who doesn't understand how I got the overall mean? Is there anyone who doesn't understand how I got the 34? To get the 34, you added all this together and divide by the number of that, which is basically going to be adding all of that together divided by 12. Is there anyone who doesn't understand how I got the 34? If you really understand how I got the 34, I need you to comment yes, or you say yes.
Yes.
Okay, thank you so much, and thank you for confirming that. Now, if I want to get it 22, 39, 41, now I need to look at the placebo. Okay, I'm going to look at all the placebo. This is placebo here. There's another placebo. There's another placebo. There's another placebo. How many placebo do I have in all? I got 4, right? So what you're going to do, you're going to do 11 plus 56 plus 15 plus 6. Okay, 11 plus 56 plus 15 plus 6. Then you're going to divide by 4. Okay, that is going to be the mean for the placebo. You're going to do the same to the caffeine. You're going to do the same to the trebomine. Okay, you find the mean of each of that. And that is basically going to you're going to find yourself getting 22, 39, 41. Is there anyone who doesn't really understand how I figured that out? Is there anyone? Okay, now if you now want to get to the subject, how do I get 19, 70, 30, 17? How do I get that manually? I'm actually going to show you now. Okay, now for subject, okay, for subject one, I'm going to add 11 to 11 to 26 to 20. I will divide by 3. Okay, for subject two, I'm going to add 56 to 83 to 71. What I'm trying to say, 11 plus 26 plus 20 divided by 3, okay, 56 plus 83 plus 71 divided by 3. I'm also going to do the same thing to the subject 3 and subject 4. That is how I'm actually going to get the mean for each class of subjects. Is there anyone who need clarification on how I got that out? Is there anyone? If you really understand how I got the estimated effect for the drug and for the subject, I needed to say yes, or you comment yes. Okay, thank you so much. This is how to do that manually. Now, after you have succeeded in doing that, this is a table that you're basically going to set up. You're going to have a subject to the, when you have the subject 1, 2, 3, 4, then you're going to have the placebo, the caffeine, the trebomine. This is just your data from 11 to 32. You understand? This guy here, you can see from 11 to 32. It's like you are rearranging that, right? And after that, the mean that you got here, you've gotten for placebo, for caffeine, for trebomine, you've gotten an effect, minus 12, 5, 7. For subject 1, subject 2, subject 3, and subject 4, you've also got minus 15, 36, minus 4, and minus 17, right? Take a look at that. Now, that is what you're actually putting right here. Okay, that is basically what you're putting right here. Okay, can you give me 1 second? Just 1 second. Okay, so that is the way that is done. Now, but you know what? Uh, the good news is this. I'm basically going to walk you through now how you can do this in R. But you know what? What I'm just doing here is just what if I ask you to compute manually the estimated effects for each drug level and for each subject level. I think I just show you how to do that. But you know what? If you really want to conduct an analysis of two-way analysis of variance tests, okay, if you want to conduct that in R, okay, on this particular data set, what am I going to do? Now, let me tell you this. We got 2 hypotheses that we actually want to find out. The first hypothesis is basically to see whether there's a significant difference in the levels of drug. We also want to see whether there's a significant difference in the subjects. I'm going to say that again. Basically, what we want to do, we in a one-way analysis of variance, we have one hypothesis, but in a two-way analysis of variance, we have 2 sets of hypotheses. Okay, and the 2 set of hypotheses I really want to figure out now is basically, to see whether there's a significant difference between the levels of the drug, and to also see whether there's a significant difference in the subjects. Okay, now in R, if you really want to practice this data set, what you're basically going to do, you need to load library. You need to load start2 data, okay, that you already have in your library. Okay, you need to load that. The moment you load that, then you just write all this code. The name of the data set is fingers. Okay, you can try that if you really want to try it. Okay, so, and you're going to have access to the data set that we were talking about. where we're trying to look at the effect of the drug and subject, okay, on the tap rate. We basically want to say, is there any significant difference in the levels of the drug, and is there any significant difference in the levels of the subject? Okay, so this is how to actually import, the data in R. Now, take a look at this. If you write T, apply, tap right, list, subject, drug, comma, mean, it's basically going to produce, you're going to have a cross tabulation. Take a look at this. This is a cross tabulation. You're going to basically see here, we have a subject here, we have the drug here. Take a look at that. One factor is occupying row, the other factor is occupying column. Take a look at that. That is exactly what we have right now. Okay, and you know what? If you take a look of the tap rates, the mean tap rate, okay, for caffeine, okay, when you apply on the experimental subject 1, okay, I just wanted to take a look at that. Now, how do we actually run this in R? Oh my God, this is looking like a multiple linear regression. You remember the other time when I was working with you on the simple linear regression, we have a response on, on the predator. And when we moved to the multiple linear regression, you know what we were doing? We were actually adding. Look at that. Take a look at that. This guy here is basically the response. Okay, drug is factor A, okay, and subject is factor B. Okay, and don't forget, what we're doing right now is two-way analysis of variance. And you know what? Take a look at what I have here, AOV. Okay, and that is going to be the difference between what you're doing now and when you actually conduct a multiple linear regression model. In a multiple linear regression model where you have AOV now, you're basically going to have ALM. Okay, you're basically going to have ALM. Okay, oh my God, when you do the summary, this is what I have right now. Okay, this is the result, this is the output. Okay, can you all confirm again if you are still hearing me clearly? Can you all confirm again if everyone is still hearing me clearly?
Yes.
Okay, thank you so much. Thank you so much. If you really understand what I've been explaining today, I need you to say yes, or you comment yes, if you really understand. I think I only see one person that say yes. I'm going to make an announcement again. If you really understand what I've been presenting today, I need you to say yes, or you comment yes. Okay, thank you so much. But is there anyone who need clarification? Is there anyone who want to ask question, who need clarification? Is there anyone? You can actually make a comment, or you can actually chat with me. Okay, that's no problem. I think I'm okay with any of that. Okay, now let me tell you this. I want to say on our non-hypothesis is trying to tell you the drug, there's no significant difference. Okay, there is no significant difference. Okay, in the levels of the drug, okay, in the drug levels. Okay, and why the alternative is going to say there is, right, there is a significant difference. This is for factor A. Okay, that is hypothesis for factor A. Now you're also going to have another hypothesis this time around for factor B. Don't forget, your factor B is the subject. Okay, now you're going to have H naught. Okay, you're going to say there is no significant difference, okay, in the subject. Okay, and why the alternative is going to say there is, okay, significant difference. I told you, you're going to have two sets of hypotheses when you are dealing with the two-way analysis of variance. If you're dealing with a one-way analysis of variance, you're basically going to have one set of hypotheses. But in a two-way, you're going to have two set of hypotheses. Now, let us now look at results. Take a look at it. This is a drug, right? Look at the p-value here for drug. Okay, at a 0.05 level of significance, this p-value here associated with drug is less than 0.05. And you know what? What are you going to do? You're going to reject the non-hypothesis. Rejecting the non-hypothesis means there is a significant difference in the levels of the drug. Don't forget, the drug is a placebo, the trebomine, and the caffeine. So it means the rate, the rate, the response we're comparing now, okay, is statistically significant. It means there's a statistical significant difference, okay, between, between these levels of drug when you are putting into consideration the rates, the tap rates. Now, what about the subject? For the subject, you're basically going to see that that is also less than 0.05. And what does that mean? That actually means there is a significant difference in the level of subject as well. And you know what? When the subject is significant, and we did not consider that in our model, if you have opted for one-way analysis of variance where you only consider drug alone, then you could mislead. Okay, you can only mislead if and only if the subject is significant and you don't really consider that in your model. You remember what we did in linear regression, where I actually stress on the importance of the covariate. Okay, so right now it means we're actually justifying inclusion of subject. Subject in this case is what we call block. Okay, that's a blocking factor. We introduce blocking in experimental design when the experimental units are no longer homogeneous. Okay, that is the reason. Okay, now the next thing I actually want to do now, we've rejected the non-hypothesis in the drug and in the subject. But you know what? What I want to show you now, I basically want to show you the model for two-way ANOVA. This is the model now. Take a look at that. You know, this guy here is the effect of factor A. Okay, like in the example that we just treated, factor A is basically the drug. And why beta J is the effect of factor B, which we call the subject. And this guy here, of course, is a random component, which you only going to find in any statistical model. And this guy here is basically the overall mean. Okay, you know what? Just like in the other statistical regression model, even in analysis of variance model, whether one-way, two-way, or factorial design, we expect that the error time to also follow normal distribution. Okay, we expect that the error time also follow normal distribution. Okay, so when you take a look at what I have there, that is two-way model for two-way ANOVA. Okay, we also have model for two-way ANOVA with interaction. You remember in the multiple linear regression that we did the other time, at time we could have situation where interaction effect can also be incorporated in our model. Oh my God, take a look at this. This is for factor A, this is for factor B, and this guy here that I actually call gamma kj is a combination of the two factors. Okay, is a combination of the factor A and factor B, because there's possibility that the two factors will interact. Okay, and because of that, I'm basically going to tell you now we got two types of two-way ANOVA. The first one here is the two-way ANOVA model without interaction, and the second one here is a two-way ANOVA with interaction. You know, just like what we normally do in the regular regression class where we actually compare multiple linear regression model with interaction with we compare that with a multiple linear regression model without interaction. We've done that before, right? We're also going to do the same in analysis of variance, where we have two-way analysis of variance with interaction and two-way analysis of variance without interaction. Because let me tell you this, even though you've introduced blocking effects into your model, if there is interaction between the factor A and the factor B, okay, we also need to investigate that. Because you know why? We always look for a way to improve on our model. We can never get satisfied, okay? No matter how we try, the error can never be zero. And that is the reason why we're always going to have, every opportunity to improve on our model. Okay, and I'm also revisiting the one-way model. I just want you to see the difference between the one-way analysis of variance model. This is just a factor A, but when you look at this is a two-way analysis of variance with interaction, and this is a two-way analysis of variance without interaction. Now, I want to go into the ANOVA table now. I want to show you how the ANOVA table is basically going to look like when I'm considering two-way ANOVA with interaction. And when I'm considering that without interaction, take a look at what I have right now. This is the way ANOVA table is basically going to look like. Okay, we're going to have factor A, factor B. We're going to have interaction. We're going to have error, and basically these are the degree of freedom. This is the sum of squared, this is the mean squared, and this is f. And you know what, there's a relationship between them. I basically wanted to see when I do SSA divided by the corresponding degree of freedom, that is basically going to give me the next column. When I do SSB divided by that guy, I'm basically going to have this. When I do this guy here divided by that, I'm basically going to have this. When I do this divided by that, I'm basically going to have this. Take a look at that, okay? And if I want to get my F, what I'm going to do, I'm going to say MSA divided by the mean square error, okay, which is what you actually have here. Then MSB divided by the mean square error, that is what I have here. And MSAB divided by the mean square error, of course, in a situation where I have, I incorporated the interaction effect into the model, I'm actually going to have 3F. And when I get 3F, it means I'm actually going to have three sets of hypotheses, because I'm going to have a hypothesis that tests about the significance of factor A. I'm going to have another hypothesis that tests about the significance of factor B. I'm also going to have another hypothesis that talks about the significance of interaction. Okay, so take a look at that. Okay, you know what I want to do at this moment? I want to demonstrate to you how the two-way ANOVA model works for interaction and without interaction. And because of that, I want to use a particular data set where we want to look at the effect, okay, of a particular dose of drug on the tooth growth in guinea pigs. I'm going to say that again. We basically want to look at the effects of dose of drugs, okay, the effect of dose of drug, okay, in tooth growth, tooth growth, tooth growth in guinea pigs, in pigs, okay. We want to look at the effect of that. And not only that, as we want to look at the effect of the tooth growth in pigs, we want to look at the effect of the dose of drug, okay. And not only that, we also want to put into consideration a blocking effect that we actually call the method of delivery. The method of delivery, it could be orange juice, okay, or ascorbic acid, okay. That is the supplement, okay. And you know what? For the dose, we're going to have 3 levels of the dose of drug. Okay, you actually have three levels of the dose of drug. Okay, that was why I call that the D.5, 1, and 2. Okay, when I use a drug of 0.5 mg, 1 mg, and 2 mg, which means I have three doses of drug, I want to look at the effect of that on the tooth growth. Okay, but I also want to put into consideration the method of delivery. The method of delivery is basically, we got two methods of delivery that we call the orange juice and ascorbic acid. Okay, this is just part of the data set. Okay, this is part of the data set. Now, this is the cross tabulation of that. And you know what? I'm basically going to use 60 observation. Okay, I'm going to use 10 people, 10 pigs. We're going to use orange juice as a method, and the level of the dose of drug will be 0.5. We're also going to use 10 pigs for when the dose of drug is 1, and the method of delivery is orange juice. Okay, and we're going to do it for that. We're also going to repeat the same. So definitely, what do we have here? We got two-way analysis of variance, where we're looking at the effect of dose of drug on tooth growth in guinea pigs, and also putting into consideration the method of delivery. Because if there's a variation in the method of delivery, the OJ is actually called the orange juice, and the VC is, ascorbic, ascorbic acid. Okay, ascorbic acid. Okay, those are the two methods of delivery. Okay, which I'm actually going to call the block effect, which I'm also going to call the factor B. Okay, the factor A is the levels of the drug. Okay, now the very first thing we're going to do a box plot. I told you, as part of exploratory data analysis, we're going to do a box plot. This is the code. And take a look at this now. This is the box plot. If you look at this is the length of the tooth, because we're talking about the tooth growth, and at different levels of those, and at two different deliveries. Okay, method. Okay, using the method of orange juice and using the method of ascorbic acid. I just wanted to see that. And as you can see here, we are seeing a sense of a significant, a sense of a difference between them. But the only way to tell whether the difference is statistically significant or not is to conduct a test. Okay, but right now, this box plot is actually giving us a sense of a difference between them, only that we don't know whether the difference between them is very pronounced or not. Okay, now we actually construct what we call interaction plots, because we actually want to see whether interaction exists, whether we need to incorporate interaction effects of dose and the method of delivery into the model. And as you can see here, you basically see at the time they come together. Okay, now if I want to do this in R, what am I going to do? Take a look at this. The length on the supplement, which is the method of delivery, and the dose. Okay, I'm going to run that. That means here I'm running that without interaction, right? This is the results I got without interaction. Okay, that's what I got. When I want to incorporate interaction now, take a look at this. I'm incorporating interaction into my model, and I want to see what is going to happen. Take a look at that. The interaction effect is significant at a 0.05. So which means the output here can be more trusted than the one here, because situation where the interaction effect is significant, of course, it means we needed to incorporate interaction effect into the model. Okay, that's why I have this. You know what? I'm basically going to stop here today, and I'm actually going to continue from this after the spring break, because I basically have information to pass across for the past, for the remaining 4 minutes. Okay, now the information I want to pass across, I want to say the midterm one grade has already been released. And of course, when next I come to class after the spring break, I'm actually going to bring your exam document. And of course, the average performance was 90.25%. So which is very interesting. So which means students, you have been really, I actually want to say that you've really done a very great job in the exam. You know, for you to have an average of 90.25%, oh my God, you know, you've really done a great job. But you know what? You can still improve upon that. You know, you could be targeting 100%. You know, I'm actually going to be, so I'm going to be the happiest man, happiest professor on hearts if the average the performance in my class is 100%. You know, that is going to be my joy. So, but I also want to say I give you a kudo. I really congratulate you for the performance. And if there's anyone who actually, you know, if you're not satisfied with your grade, of course, you're basically going to have your exam document, you know, distributed to you after the spring break. Okay, is there anyone who really want to ask question before I go today? Is there anyone? If you really understand what I've presented today, I need you to say yes, or you comment yes, if you really understand what I've explained. Oh my God. Okay. Thank you so much. But you know what? If there is any one of you who doesn't understand what I've presented, please reach out to me. Okay. And before you go, I also want to say this, since next week is basically, to the best of my knowledge, going to be spring break. I want to remind you that midterm 2, we cover chapter 3, 4, 5, and 6. Okay, I'm going to say that again. Chapter 3, 4, 5, and 6. And of course, the midterm 2 practice question will actually be released over the weekend. Make sure you wash out the midterm 2 practice question, just like what I did in the midterm 1. I'm also going to do the same in the midterm 2. Okay, so I'm going to say that again. The midterm 2, we cover chapter 3, 4, 5, and 6. And you know what? Today, I walk you through chapter 6. Although we have not really completed that, we're actually going to complete that, uh, you know, by the time we resume for lecture again. And again, before I go, I conducted today's class online, which I've already sent a message before the class time, just because I get exposed to somebody who tests positive for COVID, and I was trying to take precaution, and that is the reason why today's class is actually conducted online. Before I go, is there anyone who need clarification, who want to ask question? Okay, let me just quickly summarize what I did today. Today, I introduced you to a two-way analysis of variance that we also call randomized complete block design. And I told you the reason why we need to move from one-way analysis of variance to two-way analysis of variance, because assumption that we have using one-way analysis of variance is that the experimental units are homogeneous. The situation where the experimental units are not homogeneous, then it means another sources of variation has been created in form of a blocking factor, and that need to be incorporated into our model. We need to test for that blocking factor. And of course, I told you, we have the two-way analysis of variance model. We can have the one without interaction, we can have the one with interaction. And the moment we test for the blocking effect, if it is significant, then we're actually going to prefer, complete, randomized complete block design to the complete, to the one-way analysis of variance. And the situation where the interaction effect is significant as well, we're basically going to, we're going to prefer using two-way analysis of variance with interaction, as against using two-way analysis of variance without interaction. Okay, before I go today, because I cherish every one of you, make sure you stay safe and enjoy your spring break. Bye for now. You're welcome. Thank you too. Thank you, everyone. Bye for now.